This tutorial will show you how to use EDPIV to generate synthetic images suitable for PIV analysis. So you begin by launching EDPIV and then go to the processing window. And in the processing window, go to Edit, and down at the bottom of the Edit menu, Simulation. Select that, and this brings up the particle image simulation dialog box. And you choose for the number of synthetic images you'd like to create. And let's say the next tutorial that I will do is analyzing a group of images. So I will create a group of images here. So let's say I'm going to create 10 pairs of synthetic images. And then as I move down the left-hand side of this window, you come to the velocity fields that you could choose. So you could choose uniform flow and enter in various values for uniform flow. Roman numeral 2 is periodical, four-roll mill, and shear flow. So these are various different types of flows that you could choose. So periodical is essentially an array of sines and cosines with which you can make different kinds of vortices. Four-roll mill is something like immense stagnation point flow, and linear shear is essentially planar couette flow. Vortex and potential flow, Roman numeral 3, this has a vortex in the center and then potential flow around the outside. And for all of these, you enter something about how fast the flow should go. For instance, in the uniform flow, you enter the displacement in the x direction and in the y direction. And notice over here on the right-hand side, it says 1 over 100th pixels. 1 over 100 pixels. So the number that you type in here will be in hundredths of a pixel. So if I type in 500, that would be a displacement of 500 pixels in the, sorry, there would be a displacement of 5 pixels in the x direction. Down here, I'm going to simulate, well, let's do linear shear. So I'm going to simulate linear shear, and the amplitude, this would be the speed of the top surface. Well, this the top surface will go to the right at this speed, the bottom surface will go to the left at this speed. So let's make that 500 pixels. And in the case of linear shear, the shear is distributed in only the vertical direction. So the wavelength is the height between the two opposite moving plates. So I'm going to leave that at 512. As I come over here to the right, you see this is a portion of the simulation that tells you about the particle images that you're going to generate. Alright, now let me get back to that 10 linear shear, let's say 500. Now coming over here, I can change the number of particles. So it'll put 20,000 particles, 20,480 particles in my image, and I find that's a bit much. So we're gonna decrease that to about 5,000 is a reasonable number. You can choose here a mode. The mode is either quick or fine, and essentially the quick mode is evaluating the Gaussian function at the locations of each pixel. So that that's the quick way of generating a simulated particle image. The fine way of generating a particle image is essentially an integration of the Gaussian over a pixel area. All right, so I guess maybe the important takeaway message here is that fine is a more accurate way, but more time-consuming. You have a distribution. You can distribute the particles between some minimum size and some maximum size, and 2 to 5 is the default there, and then between some minimum brightness and some maximum brightness. And you can change those. These generate 8-bit images, so I don't want to make this much brighter than 256. 255 would be the maximum brightness possible. All right, variation of particle distribution. If I would like to have the particle concentration vary from one side of the image to the other, I can enter that information here. Also, I can have the velocity field that's used, or actually the displacement field that's used to move the particles. I can have that saved in a memory location. All right, so that explains the first screen. And then there's, if I go up to the top menu, there's another menu that says noise, and I can enter different types of noise. So random background noise. This is what I would call single pixel readout noise. It's just a white noise that's added on top of the particle images that are created. Brownian motion. So I can take all of the particles that were simulated, let's say the 5,000 particles that I intend to simulate, and in addition to moving them according to some well-defined velocity field, and as you know, I chose shear flow. In addition to that, I could add on top of that a component that is Brownian or random. Again, a white noise process, and this is in pixel percent, which means hundredths of a pixel. So if I wanted the Brownian motion to have an amplitude, an RMS magnitude of 2 pixels, I would type in 200 here. And then low frequency background noise. This is used to simulate the kinds of variations in lighting that you would find in a real experiment. So I could enter how strong that variation should be in gray levels, and then the wavelength in the X and Y direction. All right. So for this simulation, I'm not going to add any of those effects on. And I'm ready to go, so I'm going to click OK. And you can easily generate a lot of images. And so it says, are you sure you really want to do this? So I'll say yes. And then it pops up a dialog box. Where do you want to put it? So I'm going to put it in this folder. I'm going to create a new folder, which I'll call simulated sim images, and I'll select that. And now I enter a file name. Let's call it shear, and click save. And it's busy running right now. I can come maximize this window with my simulated images, and you can see that I have my 10 particle image pairs, and one of those is placed in the active memory. Okay, so that's it for showing you how to simulate how to simulate particle motion, how to simulate images that show particle motion.